for coming and presenting on supersolidity of a dipolar Bose gas and introducing it to Blair Blakie.
Thank you very much, and thanks to the organisers for the chance to come here and hear about a lot of the developments happening in the field. So I realise I'm standing between people and lunch, so I'll try to get underway.
We never had that before.
I think that I don't share, so.
Yep. Okay, great. Sorry about that. So to begin with, I'll just acknowledge some of my the people who helped out in what I'll talk about today. So Danny Bailey's a long-term research fellow in the group. This collaboration actually started with lots of discussions with Lorianne and Francesca, and Joey Smith is a PhD student who finished up recently in my group. So I'll talk a little bit about supersolids today. And of course, supersolid is a phase of matter possessing crystalline order and superfluidity. And work in this area goes back about 50 years. I won't go over much of the history, but if you look under the Wikipedia page of a supersolid, it lists these wonderful developments in cold atom systems. And so particularly these from the last speaker's group, the use of cavities. Also spin orbit coupling down the road at MIT. My focus will be on these dipolar VCs, and so there's some really nice developments in about 2019 with 3 groups realizing these supersolids in dipolar VCs and cigar-shaped potentials. That's now moved from sort of these one-dimensional lattices onto 2. And of course, there's also work from material precision today with having 2D VCs. So I will briefly mention the motivation being these nice experiments. So I borrowed some images from the 3 groups that first realized these. And so the basic scenario seen in these bipolar VCs is to find them in some cigar-shaped potential. Then by lowering the S-wave scattering length, the system smoothly modulates into a supersolid and maybe through isolated droplets. And so there was these 3 experiments using very similar geometries and these magnetic atoms to realize this in 2019. Initially, these experiments had somewhere between about 3 and 5 droplets, but I guess with that's up to 4 to 10 or so in some of the more recent experiments. So what's the properties of these supersolids? Well, firstly, the D equals one-dimensional or one-row supersolids. They're of the cluster type. They're typically thousands of atoms per unit cell. They're described by these extended mean field theories, where the standard mean field theories augmented by quantum fluctuation effects. Interestingly, the experiments in this area all need to be accompanied by quite large-scale numerical calculations to help interpret the results. And still a few questions that sort of come up in some of this early work. The transition between the VEC and supersolid looked to be continuous and discontinuous, and that was judged from the numerical calculations. But more recently, experiments have looked at change confinement and have seen, by ranking across the transition, evidence for, depending on the conditions, continuous and discontinuous transitions. So a little bit of a trip down history on some related work for these D equals 1 supersolids. There's these soft core interactions. And so a model some time ago, looking at this, was sort of one-dimensional mean field model, where there is the soft core interaction of some strength U naught in some range A. And if one defines this parameter lambda, only depends on the density and the interaction parameters, then there is this It's a very simple phase diagram where you go from a uniform ground state to a spatially modulated state at some critical value. And in this work, the rotor excitation was observed to play an important role in destabilizing the uniform phase. And in this one-dimensional case, the transition is second order, whereas in high-dimensional cases, for the soft core interactions, it's a discontinuous transition. So the other system that turns out to be something that we realized within experiments was these spin orbit coupled systems. And so for the case of a 3D pseudo spin half and two component system with this Raman-induced spin orbit coupling. So in the case with a single particle term looks like this, then you get these sort of nice phase diagrams here from the Truncated group showing as a function of the density in the system and strength of the Raman coupling. There are these sort of three distinct phases. These upper two phases are all translational invariant, but the lower stripe or superstripe phase breaks translational invariance and classified as a supersolid. And although for slightly different parameters, taking some sort of line and changing the coupling strength here, one can actually see the superfluid density in the system changes discontinuously. So certainly here, transition to the superstripe phase in the phase diagram is discontinuous. There is a roton in the system, but because it's discontinuous, it doesn't, it's not necessarily related to the onset of the supersolid. Turns out there's quite a lot of things understood for these spin orbit coupled systems. There's two gap excitation bands in the supersolid state, and so this work by Truncated group. See these lower two gap bands, don't worry about this dash line or something else. One of these bands has predominantly spin density character, whereas the other one has density character. And if you look at the static structure factor, also the density band dominates the static structure factor at low K, although the spin band actually diverges causing at the band edge. And also the system, you can look at the speeds of sounds for these two bands, and we have these two speeds of sound associated with the density and spin bands up to the point where there's the discontinuous transition. So for the case of these dipolar systems, there's some very nice early theory by Racuzzo and Ansalotto. So they made a description of the system in the torus, which removes some of the finite size effects. And they showed there was a roton softening in the BDC close to where the supersolid transition occurs. They confirmed that there are these two modes again here, often called the phase mode and the phonon mode. The phonon mode or the density mode are related to the classical crystal dynamics of the system. And also they found that there's a weakly discontinuous transition here. So this was a very important paper, and I think motivating our understanding and motivating us to look at this a little bit more carefully. So the sorts of things we've been working on is to perhaps understand a bit more about what the similarities and differences are in the dipolar case from the spin orbit, the D1 situation. So, particularly what's the nature of the phase transition in the thermodynamic regime, how does it depend on the density, and here's the phase diagram. How do the excitations behave across the transition, and how do the speeds of sound behave? So here's a sort of brief outline. I'll quickly introduce dipolar gases. We've already had some nice introduction this morning, so I'll go over that reasonably quickly. And then I'll introduce this infinite tube model. So this is sort of a thermodynamic regime model for the regime these experiments we're looking at. And I'll present sort of full numerical treatment and this quite simple reduced theory, look at some phase diagrams, and then the excitation. So we've already met these three characters. So these magnetic atoms can be characterized or introduced as dipole length, ADD, related to the magnetic moment squared times the mass of the atom. And so particularly for these lanthanides, you get quite a large dipole length. Of order 100 Bohr radii, and so this makes the system sort of interesting. That our low energy interactions characterized by this S-wave scattering length, and this dipole term, of course, is long range and anisotropic. So without much in the way of introduction, the extended mean field theory for these systems sort of goes through the standard mean field theory with a single particle and two body interactions. But there's this additional term, which called the LHY, Li-Hong-Young term, driving the leading order effect of quantum fluctuations in the system. And so this turns out to be pretty important in the regime of the dipole predominant, and the system can undergo mean field collapse. Okay, so we could ask, why do these bipolar gases in the bulk want to crystallize? And so I'll introduce this kind of key parameter of solid DD, which is the ratio of the dipole interactions to the contact interaction. When that solid DD is greater than 1, the dipole interactions dominate. And actually, mean field level of the system is at best metastable in this regime. But when you include the formal fluctuation effects, you will often find these formal droplet states stabilized. So the system elongates along the direction of the dipoles polarized, but the quantum fluctuation effects stabilize it from the mechanical flux. Without a trap, when you're in this regime, a single large droplet is energetically preferred. But when you have a trap in the system, initially the droplet's very small compared to the sort of trap. Then the droplet basically doesn't appear. You can get these self-bound droplets. As you add particles, your droplet will get larger, and somewhere along the way, if you're in the sort of case where the trap's confining along the directions the dipoles polarized, there'll start to be an energy cost here, and it'll be favorable for it to subdivide into two smaller droplets, which will repel and separate. So these sorts of cases, for a trap of the right geometry and enough atoms, you can get these sort of crystalline states for the system. So these are the sort of ground states. In this case, this certainly isn't a supersolid because these droplets are far apart and there's no tunneling between them. So the infinite tube model I want to introduce is a very simple model. We take a system where we have a zero temperature bosonic dipoles polarized along tight directions. We only have transverse harmonic confinement. I'll consider it to be sort of infinitely long. And the thermodynamic regime is specified by us specifying the average linear density along the system. It won't be fixed in general because the system will modulate, but on average it has some fixed value n. And then we want to understand what are the ground states of the system as a function of that density, and we'll look to minimize this extended mean field theory, the energy per particle, and so we'll take some unit cell in general, and we'll minimize the energy subject to the matter field in that, and also the size of the unit cell. So perhaps the point worth making is that for classical crystals, you have integer number of atoms per cell, and so the number, density, and lattice parameters are not independent. However, in these sort of typical cold atom supersolids, with a large number of atoms per site, the lattice parameters and the average density are in principle independent parameters. So one of the tough things about this business is that we actually need quite accurate calculations to make some judgment about the phase diagrams. So typically we need to resolve energies to 10 to the -6 relative accuracy or better to actually decide transitions are continuous or not. And so this domain puts a few constraints and demands on our calculations. And so I can get into the technical side of this for a couple of slides. So we use spectral methods, and also the critical tool is the careful treatment of the dipole interactions. And so what everyone in this business tends to do is, when you want to evaluate the dipole-dipole interactions, you make use of the convolution theorem. So nice thing is that the dipole kernel, you can analytically transform the dipole-dipole interaction as this very simple form in reciprocal space. And if you notice, this form actually doesn't depend on the magnitude of the wave vector k, only on this angle, but it is singular at the origin. So hence one can evaluate this by using the convolution theorem. The problem is you have, once you start using convolution theorem, you have interactions between copies. And so while we might want to kind of model one of these linear chain supersolids using a single unit cell, let's say this red droplet here, and I'll solve that in some computational box like this. Clearly, I want it to have interactions with all the other neighbors along the linear chain, but it's also going to have these copies in the transverse direction, and it's going to interact with those as well. And so the way we can get around that is by replacing the bare dipole-dipole interaction by a radially cut off one, which is equal to the bare one within some transverse radius and set zero otherwise. So basically this cuts it off to some domain like the cylinder shown here, so we get none of these interactions with copies outside, but we retain all the ones along the chain, the one-dimensional chain. And interestingly enough, for this result, it's one of the few cases where there's a nice analytic form, so it's a modification of the bare dipole-dipole interaction by these functions involved in vessel functions. Just as a bit of an example about how this works, if you take some particular ansatz for this and have a go, calculate the dipole energy as an analytic result for this. This is a simple Gaussian case. If you compare using the bare dipole-dipole interaction against the truncated, as we logarithmically change the range of the grids, you can see the bare energy converges at about r to -4, so pretty slow convergence in grid size, whereas this one converges to numerical accuracy quite quickly. So this is a really useful trick that we wrote about in this paper this week. The other thing we can actually do is introduce a bit of a simpler theory that in practice one can calculate with very modest tools. And so we call this reduced theory. One defines a field along a lattice and some simple variational description in the transverse direction. And so basically in this variational Gaussian, we have some anisotropy and some geometric mean with the variational parameters. And so you end up with quite a simple reduced theory with some single particle description of the transverse degrees of freedom and this reduced interaction. And actually, this all the interaction sort of key to making this easily computable. You can take the reduced field and actually make a fully variational treatment by introducing, let's say, another order parameter. In this case, theta would represent spatial modulation. So when theta is 0, it's a uniform state, and when theta changes, it's spatial modulated states. Okay, so these transverse degrees of freedom are quite important, and really have to emphasize that these 1D supersolids in this form are really three-dimensional systems. And so here's a little bit of an example. This is for a sort of dysprosium case with pretty typical sort of 150 Hz radial confinement. And this is an example of a ground state just below the supersolid transition. In this case, even though the trap is radially symmetric, the ground state is pretty distorted. And if you look in terms of the RMS width of the state, then the anisotropy or ratio of them is about almost 4. So it's much greater than what you would expect if it was quasi 1D. And the geometric mean is about twice the homogeneous ground state. So certainly these states are very three-dimensional, and those transverse degrees of freedom are playing an important role. And really what we're seeing here is that in the sort of tube-like traps, cigar-like traps, there's very significant magnetic friction occurring in these states. So typically the state's going to start becoming highly anisotropic to reduce the dipole energy. So if I use this reduced theory, we can actually come up with phase diagrams quite readily. So varying the sort of average density in the system, and this is showing the space scattering length you need to reduce to C modulated state. So here what I'm showing, my order parameter is this density contrast, which just characterizes the contrast of the density along the tube. And so where that takes the value of 0 up here, we're in a uniform BEC state, and then we see that it develops a modulation. Turns out that this transition is continuous for an intermediate range of densities. So from some sort of low to high density, the transition develops continuously. And the outside of that range, it's discontinuous. And so, of course, this continuous nature of the transition is probably one of the features that made the system quite readable, accessible to experiments ramping over the transition from the BEC into the supersolid. The other thing I've shown here is actually this red line shows the point where the roton softens in the uniform state, which coincides over the region where the transition is continuous. We could ask how reliable is the reduced theory. Well, it wasn't until that reduced calculation from about 3 years ago. It wasn't until this year we actually managed to repeat that without the approximations. And so compare basically this black line with this gray line. So there's a sort of systematic shift of about 2 ball radii where you predict the transitions. So that's, but otherwise qualitatively, this region of continuous transition is very similar between the two predictions. So I've talked about the development of crystalline order. Well, superfluidity is another important aspect. And so Liggett actually looked at this in a couple of papers, asking the question, under what conditions is a zero temperature quantum system 100% superfluid? And in order for it to be 100% superfluid, one of the key criterions is the Hamiltonian is invariant under translation and time reversal, and neither of these invariances are broken in the ground state. Well, of course, once you have this crystalline density forming, we've broken the translational invariance, and so we no longer expect superfluidity to be 100% even at zero temperature. So there's a couple of ways to, one key way to quantify the superfluidity in these systems, and that's, for instance, the non-classical translational inertia. So basically, what's the momentum of the system when you're in a slowly moving frame? Liggett actually developed a couple of bounds for this that work extremely well in these D=1 supersolids. So there's a lower and upper bound just based on the ground state wave function without moving frame. And so, as I say, these bounds are pretty tight, usually within 1% of actually calculating this translational inertia. So we can look, and in addition to the density contrast, look at the superfluid fraction and for these systems, and this allows us to look and sort of decide qualitatively whether the supersolid is. Because within these extended mean field theories, it's not possible to decide where you should delineate the transition to insulating droplets, but there's been recent work in this direction by Hans Peter's group that I'll draw your attention to. All these calculations were done for perhaps a particular confinement. You can actually look at how the scaling occurs. And so this graph's a little bit funny, but it shows the low density and high density point. That's the range over which the transition was continuous as we change the confinement in the system. So there's some results here from a few phase diagrams for dysprosium and erbium. So we scale these in terms of the fundamental dipole length in the system, ADD, and the associated frequency, and we see these all collapse. And so this phase diagram is relatively universal for these practical geometries. So having sort of got a phase diagram for these systems, I'll talk a little bit about excitations. And so we can look at these quasi-particle excitations on top of the state. Now, once you get into this modulated state, then of course, we have to describe these in terms of Bloch's theorem, and we can obtain these by solving these sort of extended Jens equations. So, firstly, on the BEC side of the transition, so we're in the uniform state, it's destabilized by rotor mode softening. So this is the lowest energetic band, and as the scaling length decreases, we see this roton form, and it softens down at some point. In fact, if I look at the energy of the roton and its wave vector, we can extract out these critical values where it goes soft in this sort of case. Also turns out this wave vector sets the initial pattern of the supersolid that forms. So I've plotted here again this roton sort of dispersion relation in the uniform state right at the critical point. And so here I'm considering some density and crossing the phase diagram and right at the critical point here. Just for reference, I colored these parts. I can fold them back into reduced zone scheme. So in this case, the reduced zone is defined by the roton wave vector. And so you can see how those parts fold back. You can also see that in the uniform BEC, we have a single Goldstone branch. So now let me take those results. They'll show if we lower the scaling length a very small amount. We now develop a ground state that has about 10% density modulation. The excitations now some avoided crossings, which is a little bit complicated. Go a bit deeper in, lowering the scaling a bit more, then we get these nice separation of branches. So we see clearly 2 Goldstone branches. As I mentioned earlier, these were referred to as the phase and density branch. Also, one can identify this third branch as a Higgs-like amplitude mode of of the crystal modulation. And going deeper, these branches separate out more clearly. So, and of course, we can identify two speeds of sound here, and I'll show some results for the behavior of these speeds of sound shortly. We can also look at density fluctuations, and so this via the static structure factor. For the case where it's uniform, in the spherical column, you can see that there's a divergence at the zone edge as expected. The density branch carries all of the weight. Of course, in this case, the momentum is a good complement number, so only that red branch can contribute. But once we go on to the modulated ground state, in the cases where there are these sort of interesting crossings between branches, you can see, well, it's pretty complicated here, but once we get into these well-defined branches, then the density branch carries all the low momentum weight of the density fluctuations in the system. So a couple of other characteristics. So if I cross the transition here from the BEC side to the supersolid side, we can see the behavior in the superfluid fraction and the density contrast. We can also plot the energy gap of the roton, and on one side, and on the other side, we can look at the Higgs energy, which is the energy of this third branch at K0, so that comes down on the other side to lead to the transition. And we can look at the speeds of sound. And so here we've got a single speed of sound on the BEC side, and then we've got these two branches on the other side. And just for reference, all these dotted lines are just comparing this full 3D calculation to that simple reduced theory. There's also a critical velocity here, defined by the Landau criteria. It's basically the roton energy over the roton momentum. You might ask, what's the critical velocity in the supersolid? That's a little bit harder. We haven't looked at that yet, but there are schemes to do that by basically looking at the excitation spectrum and moving frames. Now, could I ask what's happening here to the speed of sound? In fact, we had looked at these speeds of sound many years ago, actually in the reduced theory, and certainly in the reduced theory, you can see they don't really match up. So we're a bit worried about what's happening there. And the way we can understand maybe a little bit of what's going on is to look at the compressibility of this of the system as it goes across the transition. And so the usual relationship between sound and compressibility that holds for BEC is this that compressibility is related to 1 over MC squared, where C is the speed of sound. Of course, you can calculate the compressibility by how the density changes with respect to the dynamical potential. And so let us just have a look. Let's say this region where the transition is continuous, we'll go across the transition on a number of different density lines. And what one can see is that the compressibility has this discontinuous change at the transition. Although interestingly, the size of that seems to decrease. In fact, it basically vanishes at this point here, and then as we go further, it reopens up. So certainly at the top of the phase diagram, it looks like the compressibility has no jump at that point. And we can check that a little bit more carefully, define this delta kappa as being the jump in compressibility. We can certainly see, yes, it's minimized when the roton is maximized in the system. Now, you may ask, why does the roton sort of have this behavior as the system density changes? Well, firstly, it starts increasing because the two-body effects are dominating, and in that case, we don't need to be dipole dominated, or that piece rate scattering does not need to be as low. Often the roton can be the kinetic energy. But once the density gets high enough, then the quantum fluctuation effects basically act like a repulsive stabilizing effect, and that starts to lower that transition there. So usually on this side, basically quantum fluctuation effects should become more important. Okay, so the compressibility, of course, relates to the speed of sound, and one way perhaps connect to this is through the density response function, the static density response function. This is an inverse energy related to the inverse energy moment of the dynamic structure factor. And we can also look at basically how long the bands contribute to this. And critically, in the K zero momentum limit, the static density response function gives us the compressibility. And so here I'm looking at a rather low density case. how the speed of sound change across the transition, and certainly here there's an obvious discontinuity in the speed of sound. And the sort of solid line I'm showing here is the scale compressibility. It's what the speed of sound would be if it obeyed this very simple relationship. So you can see on the BC side, that's certainly the case. So once we cross over, while this scale compressibility matches the density speed of sound at the transition, as we go deeper down, it certainly doesn't. And that's have a little bit of a closer look. Let's take some particular case here, and you can look and see the static density response and how contributions from these lowest two bands, the phase and the density band, are both quite significant. And so while in the K goes to zero limit, the static response function does agree with the compressibility. You can see that both of these lower bands are involved. So certainly for the compressibility, we need to take both these bands into account. So some of these things you might ask, what's the prospects for making some measurements? And sort of certainly the key tools have been demonstrated in the field. So Bragg spectroscopy is already being used to make measurements of the dynamic structure factor in these in the Innsbruck group. The other possibility is looking at number of fluctuations in the system, and if we measure the number of atoms in some cell, then the fluctuations in that relates to compressibility, at least if the cell size is large enough that in the thermodynamic regime. The other possibility is with these high resolution in situ imaging, as been demonstrated in the Fels group, you can basically Fourier transform those measurements to directly get the static structure factor. But it certainly be interesting to look and see if some of these effects, for instance, the compressibility revealed. So I will wrap up at this point. So consider this thermodynamic tube limit for a supersolid, and giving you a little bit of a picture of the phase diagram and actually the transition in these systems, the excitations, compressibility, and speeds of sound. And so we're kind of working at the moment on extending these ideas to 2D supersolids, where of course there's a lot more interesting structure in the crystal arrangements, and of course there's more Goldstone modes. And the other thing is really the elastic properties of these systems and connections to superfluidity. So I think it'd be really interesting to look and see if some of the ideas, particularly around anisotropy of superfluidity, to be explored. So with that, I will thank you for your attention.
Thank you for the very nice talk. I had a question about the Higgs mode that we discussed. When we studied this in the finite system, we saw that this Higgs mode is coupled to higher excitations, and we actually needed the gap of the trap to have a Higgs mode that has linear Higgs amplitude character. Otherwise, it would directly hybridize with all the other benefits. So now you are in the thermodynamic limit, and you still see the Higgs mode as an amplitude mode, or what is the character of this?
So yes, I think so. So certainly we've looked at, we go back, let's go back to maybe these here. So it's quite interesting to ask how you can characterize all these bands there in terms of properties. So we'd expect, for instance, this band here to have dominant phase fluctuations, and there are ways to look at that, and density fluctuations. The thing actually you can look at here is how does it fluctuate the contrast, and certainly it's in practice all of these bands are slightly mixed in character, but this one, even in this little regime here, still has dominant fluctuations in the amplitude of contrast compared to other quantities. So I'm not sure where
if you look at one of these Higgs modes directly or dynamically or so, you really see the normal amplitude.
I mean,
what hybridization is always there. There's no symmetry that is protecting this Higgs mode as, for example, high disease or so.
So the challenge sometimes is working out how to characterize this, because one of the issues in this infinite system, of course, the going to K from 0 some of these modes, for instance, these modes here, divergent population. And so trying to decide what their effect is, I think that's not really such a problem for these modes, but and also when you connect that then to a finite system, sometimes the behavior is not what you expect, and seems like in the finite system, some of those lower modes actually hybridize in their character in a way that doesn't happen in the fully translation variant. But yeah, I think we are quite interested in trying to understand these bands a little bit more quantitatively.
Another question?
Do you think that it would be possible to understand how the speed of sound depends on the amount of quantum fluctuation? If you treat the quantum fluctuation as a representation to your external test, for instance.
So maybe you can clarify that. So how the speed of sound depends
In the supersolid methodology. So for instance, construct the hydrodynamic formulation for the external test and treat the quantum fluctuation as perturbation and extract the speed of sound from it. Would you think possible?
I'm not sure. It'd be interesting to discuss that. There is certainly this thoughts that that as we go towards this regime, the speed of sound might become close to being degenerate. And that might be a signal of us getting to this regime with fluctuations on that. But yeah, so I think I agree that that would be an interesting thing to look in more detail about.
Any other questions?
So along the same line, have you also seen how this speed of sound should depend on the thermal fraction of the other? If you are not a people, and take, let's say, with stochastic,
Ask me in a year's time. Yeah, very good question.
Okay, good. So thank you very much.